Hey, geometry. We are talking about surface area and volumes in this chapter of all sorts of figures, and we're going to start with a real general thing called polyhedron. So polyhedron, actually, I didn't write that down. Let me get the exact definition here. Polyhedron is a space figure or three-dimensional figure whose surfaces are polygons. Okay, so all of the is put together, and as you can see that this one down here, that's a polyhedron. That's kind of a special one. It's a prism. But if you look at all the surfaces, they're all different polygons. We got some squares in there, rectangles, looks like triangles. So that's what a polyhedron is. So that they don't have to be a special type like that. They can be just random different polygons. Now, every polyhedron, and a plural for polyhedron is polyhedra, has three things. They have faces, they have edges, and they have vertices. The faces are always two-dimensional. Those are the different polygons that you will see. The edges are always segments. Those are the edges as you would think of them. And vertices are always what? Points. So, for example, when you look at example 1, and we have, this happens to be a prism, triangular prism actually, but we're not going to get to that kind of labeling today. How many vertices, edges, and faces are there? So I'm going to put them in the same order I had them up here. Faces, edges, and vertices. And then it says list them. Okay, so we're going to have quite a list. So first of all, how many faces are there? Well, there's the two triangles, and then there's the rectangle slash potential squares, 1, 2, and 3 on the top. Okay, so we have a total of 5 faces. So I'm going to do the triangles first. Triangle RUV and triangle STW. Then I got to label the ones going around. So SRVW is one. SRUT is another. And then we got this bottom one, TUVW. Oopsie. Edges. Those are all the segments now. So when you look, I kind of start with the bases, which are these two triangles. And there's 1, 2, and 3 edges there. Go to the back one, 4, 5, and 6. And then we just have around it 7, 8, and 9. So we have a total of 9 edges. Now we got to label them. So I'll start with the triangles again. So I'll do RU, UV, VR. I'll just go in a circle. ST, TW, WS. And then we have the ones going around the middle. So SR, TU, and WV. And then, of course, the vertices, as we set up here, are points. So how many points do we have? We have 1, 2, 3, 4, 5, and 6. Those are all just capital letters. So R, comma, U, comma, V, comma, S, comma, T, comma, W. So that's the easiest part. Now Euler, that's how you say that, noticed a connection between these faces, vertices, and edges in a polyhedron, which is a three-dimensional figure. We're going to talk about a formula with a two-dimensional in a moment. But he noticed that whenever you took the faces plus the vertices, it was equal to the edges plus 2. So let's look up here and see if that works right here. If we took the faces, which is 5, plus the vertices, which was 6, is that equal to the edges plus 2? It is. 11 is equal to 11. So it works. So look on page 689, because when you see the figures, you'll see why I didn't want to draw them. Now we are going to use Euler's formula to figure out how many faces it has. Okay, so we're going to just write down the f plus v equals e plus 2. And the f is what we're looking for. We were given the vertice of 20, the edges of 30, and we just need f. So that's pretty simple, right? F plus 20 equals 32. Subtract the 20 from both sides, and we get faces 12. Over here, same thing. F plus v equals e plus 2. Faces are 20, vertices are 12, edges we don't know, plus 2. Subtract the 2 from both sides, and we get 30. So that's pretty straightforward. I'm going to make sure you can see this okay. And, but if you were to take those three-dimensional figures and make it into an actual net, so you opened it up and you wrote it flat into like a two-dimensional, whoopsie, I should have circled that whole thing, net, this is then what formula would work for a net. It drops at 1 if you notice. So if you flip to 690 in your book, you will see there is what's called a trapezoidal prism there. But it says to verify f plus v is equal to e plus 2. So when you look in your book, go ahead and count the faces. Okay, I see 6 vertices. I see 8 edges. I see 12. We get 14 equals 14. It checks out. If you didn't see those, you may need to stop the video and go and recount. Now it says to take that and make a net. That can be difficult. I'm going to assume we got this bigger bottom part of it, and then we got the 3 smaller sides, and then off of that bigger bottom part comes those trapezoids. So it's going to look something like that, although, yeah, you know I'm not a good artist. But then it says once you've done this net and you got it in two-dimensional, now verify, does this work? So that gets a little trickier. The faces are simple. 1, 2, 3, 4, 5, 6 faces. And then the vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So that's pretty simple. And now we just need the edges, and there's 19 edges. 1, 2, I'm going to kind of mark them off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. Does that work? Yes. So you lose one of the points when you lie it flat. Okay, because something doesn't overlap. All right. So let's move on. We are going to move on and talk about what a cross section is. Keep your books open, because at the bottom of 690, they're showing much better than me what we're talking about with cross sections. A cross section is an intersection of a solid and a plane. So it's like them crossing. Think of a cross section as a very thin slice of the solid. So if you're going to take a very thin slice out, what would the outline, what would the out boundary look like? So if we look at this one, but first actually look on page 690. I want you to first kind of visualize what they're talking about. In the top one, they show when you cut through that triangular prism, you would get a triangle. Now, if you would cut vertically through that cylinder in problem 4, you actually get a rectangle. So there's no curves when you cut it down. If you cut it horizontally, you would get a circle. But when you cut it straight down, you're going to get a rectangle. So now when we look at this, it says a horizontal plane, so it's like we're cutting through it right through the middle here. If we cut a piece out there, if we cut it open and opened it up, what two-dimensional figure would you see? You're going to see a circle. Now a vertical plane, that cuts it directly in half. So if you cut this straight in half and you opened it up, what would you see? You're not going to see any curves. That's my hint to you. There'll be no curves when you cut it vertically like that. Think for a minute. You are going to see something that looks like that. An isosceles trapezoid. Take some visualization on this. It's kind of hard to see sometimes. All right, now let's talk about drawing a cross-section. Let's get the steps down. First, you need to visualize. That is an important piece of this because you got to see it first. Visualize a vertical plane intersecting the vertical faces in parallel segments. I'll walk you through this in a second. Then you want to draw those parallel segments. And then you want to join their endpoints and shade the cross section. So the hardest part is the visualization in my mind. So let's look at this. This is a cube, by the way. It may not look like it, but it is supposed to be a cube. Draw a cross-section formed by a horizontal plane. Okay, so right now you should be picturing chopping this horizontally in half, opening it up, and thinking about what you're going to see. Now, in order to draw it, we're first going to draw, if it's horizontal, we want to draw the horizontal lines parallel to these. Now this is about halfway between them, so I'm going to go on this back face right here and go about halfway between and draw another one. Now when you do that, excuse me, you've drawn the parallel ones, so now you want to connect these endpoints and shade real lightly it in there. What kind of figure is that? If it was a cube, it looks like a rectangle actually because my picture's off, but if it was a cube, you know that your picture would then be a square, correct? So I hope you can get these, especially some of these simpler ones. I know it comes easier to some than others. This is a kind of a mental piece, and some people that visualization piece is a little more in place at this age than others, so don't get too frustrated with this. But all right, take care, have a great day, bye.